Good morning and welcome once again to my YouTube channel, Pearson at Excel International Maths by Mr. Kamoto. And in this video, I want us to explain example 10 of topic number 8, which is integration. Example 10 of integration of pure mathematics 3, and we are on page 155. And we continue to use reverse chain rule. We continue to use the reverse of the chain rule. And in this example, we are supposed to find the integral of cosec squared of x all over 2 plus cot x cubed with respect to x. And there are some two things that we need to understand in this one. Yes, it is in the form of the derivative at the numerator, and there is fx at the denominator, because the derivative of cot x is cosec squared x. And we may confirm that from, let's see, when y is cot x, dy dx is negative cosec squared of x. So we only have to have a negative. And the fact that we must take care of the negative will give us some different understanding or approach to this question. Again, you can see the whole of the denominator is raised to power x. That means the term itself at the denominator position is not free. So we are not advised to use the natural logarithm of x. We are not supposed to assume that y is ln of the denominator, because the denominator itself is not free. It is the whole of the denominator itself is raised to power 3. So we must consider now this form to be in the form of the integral of cosec squared of x multiplied by 2 plus cot of x minus 3 with respect to x. Now we have brought the denominator at the numerator position using the law of indices, where the index is just -3. And with this, we must now assume what we have been told in example 9, that this one is already in the form of the integral of fx f prime x, the integral of f prime x fx, and we are supposed to assume fx prime raised to power n, and in this case you're supposed to take y to be equals to fx n plus 1, and then differentiate and adjust the constants. So we are supposed to assume now y is equals to 2 plus cot x minus 3 plus 1 is minus 2, such that now when we have dy dx is supposed to be minus 2, yes, 2 plus cot x, we reduce by 1, it gives us minus 3, we multiply it by now the derivative of cot x, which is negative cosec squared of x. And at that point, of course, this negative and this negative will cancel out. So we are having at the end of the day 2 plus cot x raised to power negative 3 multiplied by the cosec squared of x. Again, if we take now this one at the denominator position, we realize that it's going to be 2 cosec squared of x all over 2 plus cot x raised to power 3. And if we compare now what we have after differentiating what we suspected to be the function, after we compare what we have, it looks like we have twice what we wanted, because we have 2 cos x squared of x over, the denominator is perfect, but we wanted cos x squared of x over the same denominator. And that means we have had twice what we wanted. So whatever we took our function to be, that is y is equals 2 plus cot x raised to power minus 2, it has now to be divided by 2, and this one takes us to be, this one gives us something like the integral of the cos x squared of x all over 2 plus the cot x raised to power 3 is given by what we suspected, but half of that. What we suspected, but half of that. So um, a half of 2 uh, plus cot x raised to power minus 2, minus 2 rather, not minus 3, minus 2, obviously, plus a constant. And that is just like it. Again, please note that with this one, we have not used the ln even when this is the derivative of part of the denominator, but because it is not free, it's not just one term, then it's raised to some certain power. We cannot use natural logarithm. We just have to assume this is one term and take it as a numerator to simply have negative raised to power negative 3. And we confirm that cos x squared of x is the derivative of cot x, and therefore we are allowed to use this approach. And that is just like it. And of course, again, visit my YouTube channel, Pearson and Excel International Maths by Mr. Kamoto, and subscribe and share widely so that we can walk this journey together. All right.